gravitation says if there are two bodies separated by distance r, then between them there is a force of attraction. This force of attraction is directly proportional to the product of these masses and inversely proportional to the square of the distance between them. That is, F, you can say m1 m2 upon r square, and now when we remove the proportionality to equality, it comes out to G m1 m2 upon r square. So this is the force of attraction where G is a constant. This is G is constant and its value is 6.67 into 10 to the power minus 11. This is Newton if you have to find the units. So let's take G on one side. So it becomes F into r square over m1 into m2. So unit is Newton meter square, force unit Newton. This is distance unit is meter square, m1 kilogram, unit is kilogram. This is also kilogram. So it is 6.67 Newton meter square upon kg square. Between the two masses there is always going to be a force of attraction. This cannot be a force of repulsion. As we have the charges where there could be a force of attraction also, repulsion also, but between the two masses there is always going to be a force of attraction only. R is the distance between these two centers. If this is a point mass bodies, then certainly you can directly take it as R. If they are huge bodies, but still the distance between them is even bigger than the dimensions of their masses, still they can be taken as point masses and directly we can take it as R. But if these bodies, they are huge bodies as compared to the distance between them, then we have to use the process of integration and vectorially we add the forces on that. This force of attraction between these two masses is not dependent upon the intervening medium, that is whatsoever is the medium between the two. The force of attraction will still be governed by F is equal to G m1 m2 by r square. This is always a force of attraction and this is central force. If this is pulling it this way with a force F is equal to G m upon r square, then this will also attract this with the same force. To every action there is equal and opposite reaction, and action and reaction they are always on two different bodies. These are the central forces. F is a central force. If the masses are small, then directly this is the distance and you can do it. Even if these bodies they are huge masses, but the distance between them is even still much bigger, so that in comparison to this distance, if their dimensions they are small, so once again they will be taken as point masses and you can directly apply F is equal to GMM upon r square. You can directly use this formula. But if the distance is small and let's say these are two spheres like this, two masses like this, and the distance is very small between them, then you cannot directly use F is equal to Gm upon r square. Then every particle, every mass particle on this is going to interact with every mass particle on this body. There is attraction between this and this, attraction between this and this, attraction between this and this, between all particles, similar between this and this, this and this, this and this, this and this, and so. So over here we may have to use the methods of integration and how we find the forces vectorially. Most of the time in this chapter we shall be using this formula F is equal to Gm upon r square, which is very much applicable for the point mass bodies or the bodies whose dimensions they are much smaller as compared to the distance between the two bodies. So if we talk about F is equal to Gm upon r square, this force is proportional to the product of masses, inversely proportional to the square of the distance between them. This is always a force of attraction. This force of attraction is not dependent upon the properties of the intervening medium. This still remains as G m1 m2 upon r square. If you look over here, the value of G is 6.67 into 10 to the power minus 11 Newton meter square per kg square. So this is such a small value. So if we talk about the two blocks, each of mass 1 kg separated by distance 1 meter or 2 meter or so, this value is going to be very small because the value of G is very small. But if we talk about the heavenly bodies, where the masses they are 10 to the power 23, 10 to the power 27 or so, such huge values, then over there because the masses they are huge, this force, it becomes quite a strong force.